Good morning, everybody. Thank you for attending this week's combustion webinar. And this week it's our great pleasure to have Dr. Paul Palies and to give us a talk on reacting swirling flow physics, which is relevant to gas turbines and jet engine. So please allow me to introduce Paul briefly. Dr. Paul Palies is a researcher in reacting fluid dynamics with specializations in aeronautical propulsion research and physics of premixed swirling flames. He developed an expertise in combustion dynamics applied to laboratory scale combustors and jet engines with a demonstrated experience in acoustics, combustion, and fluid mechanics. So recently I started to work on this topic. I realized it is super complicated. He graduated from Ecole Centrale Paris in aerospace and from University of Paris 11 in mechanics physics. He holds a doctorate. Doctorate in combustion from Ecole Centrale Paris, the famous EM2C Laboratory. He was a senior research scientist at the Research Center of United Technologies Corporation. Now they are Transient United Technology Corporation now, developing passive control strategy and modeling capabilities to support Pratt and Whitney's commercial combustor program. He is a senior member of AIAA and a member of the Propellants and Combustion AIAA Technical Committee. He is currently principal scientist at CFD Research. So Paul, how are you?
Thank you, Wentington and Giguanju for organizing this combustion webinar series. I'm glad to present today on reacting swirling flow physics. And today I will cover a topic, a type of flows that are widely encountered in a gas turbine system, both for energy generation and for propulsion. So I will start with the outline of the presentation. I want to point out to the audience that this outline for today is directly extracted from recently a book I published in academic press Elsevier, and each topic can be further looked at in this book. So I will give some element of context. We will go through the combustor. We'll look at premixed combustion for combustor, what it will be to have a fully premixed combustion system. Then we will look at premixed swirling flame stabilization. We'll look at transient combustion. I will discuss swirling flame dynamics and combustion instabilities. And finally, some conclusion and perspective will be presented. So in terms of context, it's worth to remind the audience, okay, where is the combustor, where is the swirling flame? So in a typical commercial aircraft, you do have 2 to 4 engines propelling the aircraft. For each of this engine, you have a set of annular combustor that house around 20 injectors, as you can see on the top right image of this slide. And each of these annular combustor has around 20 swirling flame, 1 swirling flame per injector. And the bottom left image is a visualization of a laboratory scale combustion system presenting such swirling flame. And you can see the typical annular distribution of this flame. On the bottom right, this is a cut plane through such annular combustor, and you see the injector, the fuel injector, along with the swirler inducing the swirling flow and where the combustion occurs. So one important aspect to look at next is all the chemical physical mechanisms that are working in a combustor. So on this slide, this is a typical cut plane of a combustion chamber. but you also can see different geometrical elements that are outlined in red. So you see the compressor outlet here with the diffuser, the fuel injector, where the fuel is bring to the combustion zone. You see the liner, which is this thin metal sheet where the cooling air is conducted. You see the dilution hole there, where a significant portion of the air mass flow is flowing through to cool down the combustion product before they go towards the turbine stator, and then you see the turbine rotor downstream. In a combustion chamber, there are many chemical physical mechanisms. So there is the combustion aerodynamics with the inner recirculation zone that stabilize the combustion with the outer recirculation zone. You can have a precessing vortex core, and under unstable condition, you can have an steady release that is harmonic in nature, that can be due to vertical wave, vortex shading, swirl oscillation induced by mode conversion occurring at the swirler or at the backplane of the combustion chamber. You do have sometimes equivalence ratio oscillation occurring, and always you do have turbulent combustion and combustion noise that are at work in such system. And in specific case, you can have entropy mode that are at work and interact with the downstream turbine stator. On this slide, you can also see the various acoustic modes. So a transverse mode would be in that direction, a longitudinal mode would be in that direction, and an annular mode is in the azimuthal direction. So that set the context of our talk today. Now I'm gonna look at the various elements in the combustor, and we will look at one critical aspect that would be needed to be considered both for current and future systems. Let's say we want to design a future fully premixed combustion system. We want to characterize well what is upstream the flame, what is the composition and the pressure and temperature upstream the flame from. So to do that, we need to define the design space as the intersection of the operating condition, the combustor requirement, and the combustion physics. And that's in this center that the design space must be. So to do that, we need to remember that an aircraft has various phases of flight, and at each phase of flight, from taxi, takeoff, climb, cruise, descent, final approach, and landing, the composition of the atmosphere, I mean, the thermodynamic state of the atmosphere is different, which is modeled with the International Standard Atmosphere. And this, associated to the performance of the engine, will determine what static pressure and static temperature will be operating the combustor. So that will drive your flame speed, that will drive a lot of the physical process at work in a premixed combustion system. So like I say, as of today, there is no fully premixed combustion system, either in gas turbine, either in propulsion area. What there is, though, is there are RQL, the top left figure, rich burn, quick mix, lean burn architecture. You have the LDI, the lean direct injection, where the fuel is injected directly into the flame zone. And you have the LPP, the lean premixed pre-vaporized system, where the fuel is pre-vaporized but still injected under liquid form. So what we'll see in the perspective of this presentation is the so-called LFP injector that is not existing as of today in an engine, and that is a technology that would enable to have a fully premixed combustion system. So we will talk about it after. Now I'm gonna emphasize the role of the swirler as a key component of the injector. In each combustor, you have one or more swirler, can be radial, it can be axial, that has a strong impact on the flow field. At the first, level, the first order, swirler drives turbulence, mixing, and mode conversion when you have unstable keys. So it's a key component of the combustion system. Now we are going to look at more combustions and combustor, and I will particularly emphasize on premixed combustion. And here on this slide, I'm illustrating the what I call local contributor of stabilization. So you can see on this slide, the left panel of the figure is an average velocity field, while the right panel of this figure is instantaneous chemiluminescence image. And on the instantaneous image on the right, I superimpose the contour of the ISL, the inertial layer, and the OSL that are in red. And I also superimpose the contour of swirling jet. So this is to attempt to identify key feature on this image. Now I also superimpose some of the flame stabilization local contributor. For example, the local equivalence ratio, which will drive if the flame is locally in the lower or upper reach flammability limit, the reaction rate, which is driven by the fuel and air and temperature levels, the flame stretch, which beyond the threshold the flame will extinguish, the vorticity, which also can create holes in the flame. So all these parameters, along with the flame speed versus flow speed budget, drive the stabilization. And they can be computed on numerical simulation, and their value investigated as a function of time and space of the simulation for flame stabilization understanding. And in the next slide, I will show some results in that direction. And I will emphasize on the flame speed versus flow speed budget as a driver of flame stabilization. So these local contributors that I illustrated on the previous slide, we can look at them a little bit more. They have been widely studied in literature, and so the local equivalence ratio, here I depict 3 different cases: a fully premixed flame with a given equivalence ratio without swirl, a stratified flame where you have 2 streams of different equivalence ratio, a stratified flame with swirl, the latest case, which will create a region of inhomogeneous equivalence ratio. You can see also at the center an illustration for straight flame in premix and non-premix flame, where one component of the flow strain is highlighted, the du over dx. The top right schematic represent the balance between the flow speed and the flame speed once the flame is stabilized for a laminar case and a turbulent case. The reaction rate at the bottom left of this slide can have at the first order the mass fraction of fuel, the mass fraction of oxidizer, and the temperature as its driver. And the vorticity can create flame surface hole during dynamic, during a stabilization. So all these contributors play a role on flame stabilization, and they can be interrogated on numerical data. So before looking at their value on numerical data, I want to highlight that this local contributor, they can be due to global flow feature of swirling flow. So basically the local effects have their source from a large structure. So that's why now I'm going to present a key feature of swirling flows that we retrieve in certain circumstances in swirling flame. So the top left is an axial radial azimuthal shear layer identified by Billion et al. And you can see here clearly the shading of the shear layer here, and also the shear layer in that plane of it's with a laser sheet here, where you see the structure in this cut plane. On the top right, you can see the vortex breakdown defined and identified by SAC-PAIAA, where you can see the bubble mode, which is the axis symmetric mode where the flow recirculates due to the vortex breakdown. And you can also see the second picture, vortex breakdown spiraling, identified by SAC-PAIAA. And at the bottom left, this is the inner recirculation zone characterized by Shiji and Beer. And one main outcome were to characterize the extent of the recirculation zone and the high level of fluctuation that are reached in such swirling flow in terms of turbulence. And more recently, the bottom right is an helical mode and inner recirculation zone identified by Oberleitner et al. And all this structure can be present in swirling flow and swirling flame, not necessarily all at once, but they all drive the local contributors that we discussed before. So now I did a list under a table form of the key flow feature in swirling flow, and it includes the swirl flow rotation, the inner central recirculation zone, the outer corner recirculation zone, the azimuthal shear layer, the swirling jets, the inner shear layer, the outer shear layer, the vortex shading, vortex breakdown, and precessing vortex core. And all these flow features can be characterized by their frequency, amplitude, distribution, and if they rotate only or if they precess. All flow structure does not necessarily precess. Each flow feature depends at various extent on the geometry of the injector and the swirler. They depend on swirl number, equivalence ratio, and Reynolds number, and the flow feature, and that's one of the key aspects, impact the local quantities. So now we have looked at the effect of the global feature on the local contributor for premixed flame. We are going to look at premixed swirling flame stabilization and a recent framework that is outlined in the book I was referring to. And here to investigate flame stabilization, we are going to look at the flow flame speed budget, which is a kinematic relationship for the flame surface. And you see it represented here, which each term is defined. and we are going to associate to this kinematic budget the flame displacement speed defined from the thermal energy budget here. And what is on this slide is what term of the kinematic budget and the thermal energy budget affect the flame surface speed. So to do that, I want to explain a little bit how I proceed there. I decompose this quantity, the flow flame speed budget, into a static and a dynamic component. You can think of as splitting it in a time average and a fluctuation component. It's a little bit different, but it's the same principle. And at the top of this diagram, you see the instantaneous budget, meaning we look at the instantaneous kinematic relationship budget. And this decomposition helped to investigate the flame stabilization mechanism on the CFD data. So if I look at the first block here, the flame speed is driven by a reaction and a thermal diffusion term, and we can both quantify along the flame structure both of these terms. While the flow speed is determined by the convective effect mostly, and this combination, flame speed and flow speed, determine the flame surface speed. And we will see that in an instantaneous manner, each piece of the flame is convected, is dominated by convective effect on the swirling jet. While we can also look at this flow flame speed budget by splitting, like I said, into a time average and dynamic fluctuation, which is done at the bottom of this slide. So if you look at the static flame surface or the time average, you can see that the flame will stabilize in region where the velocity compensates the flame speed. When the flame surface speed is 0 and there is exact compensation of flow speed and flame speed, that will tell us this is where the flame stabilizes. And we can also have a dynamic budget for the fluctuation, which is expected to be satisfied when fluctuation of flow speed compensates fluctuation of flame speed. So that's the framework of the next couple of slides I will talk. But first of all, I want to highlight a little difference between the time average and the static mode, the static field. So we know the time average can be obtained from data, but we also can show that the time average is the sum of a static component and the time average of a fluctuation with respect to that static component. And when you have strong nonlinear effect, the difference between the time average and the static component become significant. This has impact, and on this slide, I'm trying to show from experimental results the difference between the time average and the static component, which is also called base flow. So for example, on the right column here, you see the red line, which would be the static component or the base flow, and you see the blue line, which would be the time average. So they are different. This is for the Equivalence signal here, for example, and velocity signal shows same trend. Pressure signal, both time average and static component will be same in that particular case. So now I'm gonna move forward, and I disregard the time average. I do the splitting with respect to the static component or the base flow. So we start with the flow flame speed budget. For each direction, we split the flow into this static component and a dynamic component. And when we equalize by order of fluctuation, so what does that mean? That means that each static component balance itself, and the fluctuation of first order interact with each other, and second order interact with each other. So we reach this system of equation where we can see that the first equation is simply the norm of the velocity vector match the square of the flame speed. So that's satisfied when the flame surface speed is 0, when the flame is stabilized. So we can take this system of equation one step further and try to do a geometrical description of this system of equation. To do that, we can represent the first equation and the third equation into two spheres that overlap. The first sphere represents the first equation, where the radius is the flame speed, and the second sphere represents the fluctuating component with the fluctuation flame speed here. So that's to be explored more, this description, and we could think of data from simulation or experiment to complete this description and overlap this data to these two spheres and verify that it holds. In addition to this description, we can recast the expression of this budget for swirling flame, and that's what is conducted at the bottom of this slide. And you see that the fluctuation of flame speed depend on the ratio of the axial and the azimuthal velocity fluctuation, and that we can find exact expression of the coefficient, and that's previously published work. And we will see later in the presentation that this coefficient K and XC can be also determined analytically. I will show that after. So now I'm gonna present a couple of results from numerical simulation where I start to explore the description of the stabilization mechanism I was referring to, the flame surface speed budget, on data. So let's present a little bit the simulation and the mesh and the chemistry that were used to explore this data. So it consisted in a water domain with two veins. Here you see the swirler vein. There is 9 million, 8.5 million cells. It's a very refined mesh in the combustion zone. Far from the combustion, it's less refined. I use a single-step chemistry mechanism here, and equivalence ratio is 0.7. And we are going to look, and I use the USCN code. So first of all, we can look at the U-range results. Here you see the axial velocity on the top left. I duplicated the results to have a cut plane here. You see the methane mass fraction, then the temperature and the heat release watt per cubic meter. And this show some of the key structure we discussed in the beginning of this talk. Now, activating large eddy simulation, we see more wrinkling of the surface, more turbulence, and this is the data I use to investigate the flame surface speed budget and the flame speed. So here are investigation of on the flame surface I look at the so-called local contributor I defined earlier. For example, at the top right of this slide, you see the magnitude of SDN, which is plot over an ISO heat release surface. I also have the reacting term of the flame speed, which is plot here, and the thermal diffusion term, which is represented on the bottom right. On the left of this slide, you see what I call the budget Z, is this relation, the flame surface speed relationship, in the Z direction, because it's a vectorial equation. And what this result tells us is that you see a strong contribution on the swirling jet, meaning that on the swirling jet, the flow dominates the dynamic. And by interrogating like that the data, we can extract what are the key stabilization mechanisms based on the flame surface speed budget. So in addition to the flame surface visualization, we can look at the ISO temperature on ISO temperature surface. We look at distribution of this local contributor, and particularly we can look at the flame speed here, which is this one, and we see that there is a peak here for the flame speed, which is reached in terms of distribution, meaning the maximum number of occurrence of this value of flame speed are occurring around 0.2 meters a second. As the flame speed increase, the occurrence decrease, but we reach pretty high value of flame speed here due to it's attributed to the strain. And by doing the following approach, we can, like I say, investigate the stabilization mechanism. Now, we have looked at the mechanism in terms of instantaneous budget on ISO flame surface. Now, we look at the static component and the dynamic component. So to do that, I attempt to extract the static component from the time series data, and this is represented here. So you see the first column, it's a front and a rear view of the flame. It's an ISO temperature surface, and you have the velocity magnitude plotted as a time average, the velocity magnitude plotted as a static component, and the velocity fluctuation. And the top equation is an approximation to attempt to extract the static mode. I'm also working on how to extract static component from time series data. So what this shows is that one of the branch of the flame is more in the lower velocity region, where the flame speed will compensate the flow speed, while the outer region is not, indicating there is a competing stabilization mechanism between the two equations we presented in the previous slide. So what I'm plotting on this slide is the distribution of velocity to be able to identify which of the equation of this system is satisfied on which part of the flame. So that's the goal of this work, and that tells that the green region here, which correspond to the inner flame, is mostly dominated by the static component, while the outer region is mostly dominated by the dynamic component. So this work will need further work, but the idea beyond this framework is to decompose the flow into a set of contributors look at this flow flame surface budget directly on the data and identify a region of the flames that are satisfied more by one or the other component of the equation. So now I'm gonna change a little bit topic. We are going to look at transient combustion now, and particularly on lean blow-off. These are recent results I will show. So first, a couple of definition in terms of transient combustion. We have unsteady combustion, which include acoustics, turbulence, vorticity, and transition from laminar to turbulent combustion. We have engine transient, where we have acceleration, deceleration, starting, ignition, and relight. And we have static stability, including static stability and dynamic stability. Dynamic stability is combustion stability. Static stability is LBO, lean blow-off, flashback, and flame stabilization. So we will look at LBO. First, I want to show a couple of diagnostics that are used both for CFD or experimental data. So you have the fast Fourier transform that can be applied to flame data to extract the frequency content that was conducted on this slide. Here you see the center data, the center plot represent the FFT amplitude peak along with the frequency associated to this peak. So that help to identify which region of the flame oscillates at which frequency and to describe the underlying mechanism. Then you have phase lock data that can be conducted at once you identify the frequency, you can actually define which frequency are the most what dynamic is described at that particular frequency. So this is done on the right of this slide for another swirling flame. And you can also implement POD or DMD analysis to detect the structure and the spectra of this structure. So that was done recently on the low swirl injector here. And we can see that it helped to retrieve the key oscillating mechanism. So now I'm gonna talk on the lean blow-off case, and you see here the work was conducted to assess the ability of flame result simulation to capture a fully premixed configuration at LBO. I use a fully structured mesh, which represent nearly 240 million cells, which is equivalent to a billion cell tetrahedron for 2 key scale, the flame thickness and the Kolmogorov scale. So here we're gonna look. You have a picture here of the combustor with the swirler who is included in the system, the central bluff body here, and some surface mesh visualization. So I'm gonna focus on the premix case of this lean blow-off configuration. There were 3 points experimentally investigated: the 0.7 equivalence ratio, 0.61, 0.57, and you can see that the 0.7 and 0.61 were interrogated with OH PLIF, and the 0.7 equivalence ratio shows some reaction OH star in the corner recirculation zone, while the 0.61 did not. It's also important to emphasize that while there was no reaction in the 0.61 case in the corner recirculation zone, you still can have OH there. It's just not OH star. And then you see the sequence of lean blowout where the OH star go to 0. That does not mean there is no OH. So here I'm gonna look at the comparison between experiment and simulation for this Lindblad data. So you have on the left of this slide the numerical profiles of velocity that are compared with the bulk flow velocity. So you see the bulk flow velocity from experiment, nearly 20 meters per second, and the profile. So by integrating a posteriori this profile of velocity, you show that you retrieve the experimental bulk velocity. So that's encouraging as a validation step. Then I look at the flame shape between simulation and experiment. So on the central of this slide, you see at the top the equivalence ratio 0.7, where there is burning in both the outer recirculation zone and inner recirculation zone. You see a lot of corrugation, a lot of large-scale wrinkling of the flame front that we capture. At 0.61, you see that again the structure of the flame is captured, and you see a key difference in the corner recirculation zone, and I attribute this difference between the fact that the experiment capture OH star while the simulation capture OH. So that's why there is this key difference. Now on the right of this slide, you see the evolution of OH, numerical simulation in red, and you see the evolution of integrated OH star in the experiment. And you see a global trend that is captured by the transient sequence we model. And you see discrepancy towards the end of the simulation. So overall, the LBO trend is captured, but the onset prediction by the simulation need further work. We have some thought and results to support what should be looked at. Now I'm gonna show a visualization and animation of the simulation with the temperature at the left, the equivalence ratio field in the center, and the OH mass fraction. It's not OH star, it's OH mass fraction on the right of the slide. And you will see a key feature, it's that the OH field is temperature is reducing as the equivalence ratio reduces, and you have an entrainment into the reversal flow of the ERZ that take place for the OH. So this reduces further the reaction of the swirling flame, and that create a sort of feedback loop that reduce the temperature further and the reaction further, and should lead to onset of LBO. So here on the right of the slide, you see the large-scale OH reduction that is trapped into the inner circulation zone. So it's a little slow right now, but I'm going to let this animation display. I hope you can all see it. So that's I'm going to stop here. After we also see some dynamics that come into play towards the end of the simulation. This is characterized by the transverse mode of the cavity. And now I'm going to look at swirling flame dynamic and combustion instabilities. So First, as an introduction, it's a review of the review work that have been conducted on swirling flame dynamic and combustion stabilities. So it starts with the work by Beer and Chigier on combustion aerodynamics in the 70s. And there have been many different reviews, both on swirling flame and combustion stabilities that are highlighted here. And this has provided a lot of advance in the field, and initial work were on characterization of the swirling flow, the unsteadiness. It has been applied to diffusion flame. Then the shift has been on control. Then on premixed combustion more, and that's more recently has been the phases. So that brings me to a review of laboratory scale combustor system. So on this slide, this is a list of uh, worldwide lab scale combustion system that are either in university, either in organization, research organization and institute. And you can see, so there are various systems. Most of those are premix operating with methane. I try to characterize the swirler that was used, the diagnostics that were used, and and this give an overview of the key landscape. More recently, this is the latest line of this table. The end phases has been on multi-injector, where you do have a set of injectors that are mimicking the annular distribution we've discussed before, or annular chamber, such as from the EM2C. So all these are advancing the state of the art. So now I'm gonna talk about flame dynamic, and these are key observation for physical understanding and modeling. And like we said before, the swirler has a key effect on the system. It has a key effect on the flow, thus on the flame. So it drives turbulence level. So it will have a key impact on wrinkling of the flame, um, and because the fuel and the chemistry is set for a given system, so then you can act on the turbulence level to change wrinkling. That will have effect on flame shape optimization for fuel burn. Then you have the mixing that is impacted by the swallow effect, and that will have impact on the equivalence ratio for partially premixed system. And then you have the swallow effect on mode conversion, as the position of the swallow is important, and it drives the swirl number wave that is downstream of this swirler. So here I have, this is from my PhD work, some research of flame dynamic and mode conversion. I will give a brief slide on swirling flame dynamic, which is driven by two key mechanisms. On the top left, this is FDF of a swirling flame, premixed swirling flame, where you see at the frequency of 60 Hertz in blue, you have very low response, while in 90 Hertz in red, you have higher response. And this work led to the identification of vortex shading and swirl number oscillation impacting the FDF. You have the flame dynamic, which is plot depicted on the right of this slide, and you have a block diagram that explain what the key mechanisms are. So I will go through this diagram. So when an acoustic wave impacts a swirler, you have an azimuthal fluctuation that is created and an axial fluctuation. They have different, these fluctuations have different propagating speed, which lead to swirl number oscillation, swirl wave, and vortex shading at the dump plane of the combustor. And both these mechanisms have a distinct heat release contribution, which determine the global heat release. So more recently, this effect of fluctuations that propagate downstream the swirler was investigated analytically, and I show that the azimuthal fluctuation indeed in a 3D with a 3D model propagate at the convective speed. So while the axial fluctuation propagate at the acoustic speed, the azimuthal fluctuation propagates at the convective speed. And as you know, the swirl number include both the azimuthal and the axial velocity, so that modulate the swirl number. And this is what you can see on the bottom right of the slide. You see a swirl number oscillation that is occurring, and which impact the flame angle of the system. So now I will go into a recent work on determining the expression of two coefficients that are in the flame speed expression. I've talked before on this flame speed expression that depend on ratio of axial velocity and azimuthal velocity fluctuation. Well, this key and this C and key can be determined analytically, and to do so, one need to equate both the flame speed taken from the thermal energy budget and the flame speed from the uh, kinematic relationship. And by doing this equalization, you get this expression here, and that lead to the analytical expression of the ratio of key and xi. And this going to be submitted to a conference soon. This show that the experimental value were closely match this uh, theoretically derived expression. So now I'm going to conclude the webinar. We have looked at the introduction on physics of swirling flame. This is an active and essential topic of research for future clean combustion and propulsion system. It has an important role in terms of operating condition and geometry for this flame. These are the key driver of the flows there. Now, in terms of perspective, I'd like to split it in terms of physics insight and clean propulsion and energy generation system. So I think we should pursue 3D and steady reacting swirling flow and flame to identify pattern and also to create the data that are required to investigate this mechanism and the stabilization, for example. So we need highly resolved simulation. We need to extract physics-based model from this data. There is a avenue with machine learning, data mining on generating this data. I talk about splitting steady static and unsteady dynamic component today. Well, there is computational tool needed to actually compute the steady base flow accurately and compute the static flow particularly. There are numerical modeling gaps in terms of understanding each of the flame stretch term on the flame macrostructure. The flame stretch is a combination of 15 terms, how each of these terms impact the flame speed, for example, or impact the flame structure. The need of transient thermal boundary condition and their impact on the flow field should be looked at. And finally, I will take a wide scope step are required toward hydrogen combustion in the combustion community. We need to understand what drive the NOx, which flow structure can be driving the NOx emission. We need to optimize the fuel burning by optimizing the premix flame burning. And there is the need of injector combustion design for hydrogen-based combustion, such as the LFP that I was talking before, but not only. So that's our path towards a clean propulsion system. So that end my talk. I want to thank you again, all the organization of the Combustion Webinar and all the attendee. And I will be glad to take a question. I see a question here. In slide 32, was it an OH PLIF or OH star chemiluminescence experiment? Well, it was. There were OH PLIF and OH star sequence plotted on this slide. So regarding the effect of swirler, either radial, either axial, so what will be the impact on the stabilization? So the axial versus the radial swirler, in terms of flame stabilization, it will depend on the effect on the local contributor. So it means on the turbulence, obviously, how it will impact the turbulence level, because you can expect to have a similar inner recirculation zone. In terms of dynamic instabilities, different swirler type, axial and radial swirler, have shown that the same mechanism are at work. It is mode conversion process that impact the flame. So they have a similar effect. I will take another question. You mentioned premixed combustion is not achieved. Is it also for gaseous fuel? Can you please elaborate a little bit more? Okay, so this question is important. As of today, there is no gas turbine premixed combustion system. At the laboratory scale, we know how to do the premixed combustion in an aircraft or in a gas turbine energy generation system. There have been no technology to do fully premixed combustion. What I call fully premixed combustion is that you have a liquid fuel that is bring to an injector, but he has a heat exchanger piece which converts this liquid fuel to a gaseous fuel. Then it's mixed with air, and it creates the premixture of your premix flame. So as of today, you do not have this type of heat exchanger implemented.
There are a couple of more questions, and one specifically is asked by Professor Bob Debo, and he's interested in, can you imagine burning hydrogen in existing combustors, no physical change of engine? That is, I think, is also a question lots of OEMs are asking.
This is a great question. As of today, okay, there is a push for hydrogen based combustion. So how we will do How we will do it? Well, we know how to do hydrogen combustion. We know it at the laboratory scale combustion. Now, the process to go towards an engine is a little bit as like that. Either you start from what is existing, either you start to develop a new injection system. So there is two paths that are possible. There is no major bottleneck to go toward a real combustion system based on hydrogen. The mechanisms may be amplified, but we know them, we know how to control them. I am personally optimistic, and I think this can happen.
Okay, Paul, thank you so much for today's great talk.
Thank you very much again, Wendy.